Hi, hello everyone. Welcome back to my channel. As you all know, I am Soumya Jia from Sri Venkateshwara College of Engineering. Today I am here to explain about quicksort and its time complexity. Now let us see the contents which we are going to study in this video. The first one is introduction to quicksort, and the next one is how quicksort works, and third one is quicksort algorithm, and the fourth one is the complexity analysis of quicksort, and fifth one is how to solve a problem using quicksort, and next is advantages and disadvantages of quicksort, and last finally we are going to study the conclusion. Now let us see the introduction part. Quicksort is a widely used sorting algorithm known for its efficiency and veracity. It follows the divide and conquer rule. Quicksort was developed by British computer scientist Tony Harrow in 1959 and has since become one of the most commonly implemented sorting algorithms. The basic idea behind the quicksort is to select a pivot element from the array and partition the other elements into two subarrays. According to whether they are less than or greater than the pivot, the process is repeated recursively on the subarrays until the array is sorted. Now let us see the working of quicksort. Partitioning, rearranging the elements of the array so that elements smaller than the pivot are placed before it, and all elements greater than the pivot are replaced after it. After the partitioning step, the pivot is in its final sorted position. Choose a pivot. Select an element from the array to be used as a pivot. This can be done in various ways such as picking the first and last or middle element. Next step is recursion. Recursively apply the above two steps to the subarray on the left side of the pivot containing elements smaller than the pivot and the subarray on the right side of the pivot containing elements greater than the pivot. Now the next one is combining. Once the recursion reaches the base case of subarrays with the zero element, the smaller subarrays are combined to obtain the sorted array. And the next is of quicksort. Next, now let us see the time complexity analysis of quicksort. The time complexity of quicksort can be analyzed as follows: the average case, worst case, and the best case. In this average case, the time complexity of quicksort is 0 n log n, where n represents the number of elements to be sorted. In the average case, analysis assumes that the pivot selection is random or uniformly distributed. The partitioning process takes linear time. 0 of n is such as element is compared to the pivot exactly once. In the worst case scenario, quicksort can have a time complexity of 0 n square. The worst case occurs when the pivot selection is consequently poor, leading to unbalanced partitions in each recursive step. The worst case scenario is relatively rare in practice and can be avoided or minimized by using randomized pivot selection or other pivot selection strategies such as median. This case worth nothing that quicksort's performance is highly dependent on the choice of the pivot and the initial order of the elements. In this average case, the quicksort is efficiently and widely used due to its average time complexity of 0 O log n. However, in scenarios where worst case behavior is a concern or when the input is already partially sorted, other sorting algorithms like merge sort and hypersort may be preferred. In the best case, it is the most balanced case. Each time we perform a partition, we divide the list into two nearly equal pieces. This means such as recursive calls processes a list of half of this size. Consequently, we can make only log 2 and nested calls before we reach a list of cell size 1. This means the depth of the call tree is log 2n, but no two calls at the same level of the call tree process the same part of the original list. Thus, each level of calls needs only O of n time altogether. Each call has some constant overhead, but since there are only O of n calls at each level, this is subsumed in the O of n factor. The result is that the algorithm uses only O of n log n time. Now now let us see how to solve a problem using quicksort. Let us go through an example of the quicksort algorithm step by step. Suppose we have the following array of integers that we want to sort in an ascending order. The integers are 7, 2, 1, 6, 8, 5, 3, 4. To apply a quicksort, we first select a pivot element from the array. Pivot element is an arbitrary element. Let's choose the last element 4 as a pivot number. Next, we partition the array around the pivot by rearranging the elements such that all the elements less than pivot, that is elementary arbitrary element. With the arbitrary element is 4. The numbers which are less than arbitrary element is we have to write towards our left side, and the greater than the arbitrary numbers we have to write towards our the right side. The partition process involves comparing each element to the pivot and swapping them as needed. Now the pivot 4, it is the arbitrary element 4 is in its final sorted position. We have divided the array into two subarrays. The elements are to the left of the pivot is 3, 2, 1, and the elements to the right of the pivot is 8, 5, 6, 7. When they recursively apply the same process to each subarray, let's focus on the left subarray first. We have to select this left subarray. Selecting the pivot element in the left subarray means arbitrary element. We have to select the arbitrary element in the subarray. The first element is 3. Now the left subarray is sorted. We have tried to now the left array is sorted. We repeat the process on the right subarray, selecting the pivot element in the right subarray, which is the last element. The right subarray is now sorted. Finally, we have sorted both subarrays, and the entire array is sorted. There is the integers are 1, 2, 3, 4, 5, 6, 7, 8. That demonstrates how quicksort recursively divides the array into smaller subarrays, sorts them independently, and combines them to obtain the final sorted array. Note the pivot selection strategy, such as choosing the last element, can affect the performance of quicksort. Other strategies like choosing the first element, a random element, or the median of 3 can lead to different partitioning and potentially better average case. Let us see the advantages and disadvantages of the quicksort. Advantages of quicksort: efficiency. Quicksort has an excellent average case time, complexity of O n log n, making it one of the fastest sorting algorithms in practice. In place sorting, quicksorts the array in place, meaning it does not require additional memory proportional to the size of the input. Cache efficiency. Quicksort has good cache efficiency due to its localized and recursive partitioning process, which can lead to better performance in the practice. Randomization. By choosing a random pivot or using randomized pivot selection, Quicksort can achieve average case time complexity even for almost sorted or reversed input arrays. Easy implementation. Quicksort has a relatively simple and intuitive implementation, making it easy to understand and implement. Now let us see the disadvantages. Worst case time complexity. In the worst case scenario, when the pivot selection is consequently poor, Quicksort can have a time complexity of O n square. This occurs when the array is already sorted or contents may duplicate elements. Unstable sorting. Quicksort is an unstable sorting algorithm, meaning it does not guarantee the relative order of equal elements is preserved during the sorting process. Dependency of pivot selection. The choice of the pivot element can significantly affect the performance of quicksort. If the pivot is not well selected, it can lead to the poor partitioning, which impacts the overall efficiency of the algorithm. Recursive overhead. Quicksort relies on recursion, which can lead to high memory consumption and potential stack overflow issues for very large input arrays. Non-adaptive. Quicksort's performance is non-adaptive to partially sorted or nearly sorted arrays. It does not make advantages of existing order in the data, unlike some other sorting algorithms like insertion or merge sort. Let us the conclusion. Quicksort, which with its efficiency in place of sorting and cache efficiency, remains a popular choice for sorting large data sets, while it has a potential worst case time complexity and sensitivity to pivot selection. The algorithm's advantage and partial applications make it a valuable tool in various domains. Understanding the algorithm's strengths and weakness and performance characteristics allows developers to leakage quicksort effectively in solving sorting problems. Thank you for watching my video. Please like and share.